Okay, so today I actually have something I want to show you in our calculator looking at scatter plots and stuff. So I'm going to be going back and forth between this screen and the calculator screen quite a bit. And I'm going to be kind of going fast through some of this. I'm just expecting that you guys already know how to make things like a scatter plot or a residual plot and things like that. So if you are still sketchy on how to make those types of plots, then you might need to pause this and refresh your memory on how to do that, because I'm not going to slow down and reteach it. I'm just going to expect that you guys know it. But what's interesting is that we often use these scatter plots to make inferences on things. As you saw, we did that with confidence intervals and significance tests. But let's take a look at some other interesting scatter plots that we may encounter. You know, normally I've said that it has to be a linear scatter plot to do anything with that information, but now we're going to look at what happens if it's not linear. You may notice that there is no due portion for your homework tonight. I do want you to read the homework though. I want you to read. The due portion will come tomorrow, so you technically have a night off of doing any work, but I do want you to read the lesson. Okay? So let's take a look. Mrs. Blair's son was trying to open a bag of M&Ms when they spilled all over. But before picking up the M&Ms, he ate all the M&Ms that were face up, with the M showing. When he finished, he put the remaining 30 M&Ms back in the bag. Mrs. Blair decided to make this into a game with him to practice his counting skills. So she dumped the 30 M&Ms onto a plate and let him eat the M&Ms with the M on top again. This time there were 13 left. We repeated this process until the M&Ms were gone. So here's a table showing the number of M&Ms remaining at the end of each course, at the end of each meal, I guess. So on course 1, we had 30 M&Ms, okay? He ate the ones with M on top, and then we kept going. 30, 13, 10, 3, 2, 1. All right, that's how it ended up going. Let's draw a scatter plot of that. So what I did is in my calculator, I already have it listed. I put the course number in my list 1 as the explanatory, and I put how many M&Ms he had left in list 2. So to make a scatter plot, second scat plot, I'm going to choose the scatter plot option, list 1, list 2, zoom 9. So there is a picture of the scatter plot. So let's go ahead and draw that in our notes. Draw the scatter plot here, and you can always pause this at any time to draw the picture you see in my calculator. But if I'm going to draw this, here's what I did. As you can see, the dots kind of follow something a little like this. Okay, not very good dots, but you get the point. Remember that what we had for list 1 is the course. That was list 1. And on the side here, we had the amount remaining. Okay, we had that in list 2. But let's go ahead and draw a residual plot of that, because it looks like it could be linear, but it's not like a great picture. So I want to see what a residual plot is. I want to make sure that it's linear before moving on. So to do a residual plot, I'm going to run the least squares regression line. So we've got, I'm going to run it to option 8. And remember, the only reason I'm doing this, yes, it's going to give me the regression line, as I'm going to write that down here in a second. In fact, let's go ahead and write that now, because it's in the notes. The next thing says, find the least squares regression line of this data. So with the calculator, as you can see, here's my y-intercept, here is my slope. So we're going to write that into the notes. I'm going to say y hat equals 28.33 minus 5.29x. Okay, where x is the number of M&Ms remaining, y is the, x is the course number, y hat would be the M&Ms remaining. Okay, and since we're at it, what's the correlation? If you look back at here, correlation is the r, so it's negative 0.9. Negative 0.9. Now, you always want to run this least squares regression. You want to run this program because every time you run the program, it stores the residuals for you. So I'm going to go back to my list. I'm going to plug my residuals into list 3. This is, again, what I'm assuming you already know how to do. And I'm going to do a residual plot, which is a scatter plot with the explanatories against the residuals. Okay. Now, what do you see in this residual plot? Is there even scatter? Or do you see a pattern? To me, I see a curved pattern, which if you remember from the beginning of the year, curved patterns are not good in a residual plot. What that means is that the scatter plot was not linear to begin with. In fact, I didn't draw it real great here, but you may have noticed that it's kind of curving this way. It's not actually that linear. So if I draw the residual plot to reference that, you have the y equals 0 here. We've got a dot here, about here, 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 about right here and here. And again, you can kind of see that curved pattern in the residual plot. Residual plots are not good. Okay, and again, this is list 1 against list 3, which is the residuals. That's how we plotted that. So does the data appear to be linear? I would say no. The first one kind of looked linear, but when we looked at the residual plot, I would say the residual plot shows a curve. So what does it look like? If it doesn't look linear, does it look like something? Think about other math classes. Think about what happens when if it's really high and then all of a sudden it drops and starts to even out. It's called an exponential. So this is actually not a linear form. And back in the beginning of the year when we didn't have linear, I said, you know, we can't really find any other information. We need it to be linear in order to keep going. Well, this is an example where it's not linear, it's exponential, but now I'm going to be able to keep going. So, here's what I want to do. If it's exponential, I don't like the idea that it's exponential. Let's try taking the inverse of the responses. Do you remember what a inverse of an exponential is? You all had to at least pass Math 3 to get to this class. And I know in Math 3 you learned this. But the inverse of an exponential, I'll remind you, inverse of an exponential is a logarithm. Yes, we're going to do some logarithms here. I know that sounds scary, but it's not as scary as it sounds, okay? So we're going to find the inverse of an exponential. Basically, we're going to do logarithms. So here's what I'm going to do. We're going to take the log of the responses. So basically we're going to do like log 30, log 13, log of 10, log of 3, log of 2, log of 1. What we're hoping to do is we're hoping to undo the exponential shape by doing the inverse of a logarithm. So I'm going to go back to my calculator and I'm going to show you what I mean by this. Okay? So I'm going to go ahead and just delete out my residuals. I don't need those right now. But what I wanted to do is take the logarithm of the responses, which is list 2. Well, the fast way to do that is to scroll all the way up, and we're going to hit log of list 2. So what it's going to do is it's going to take the logarithm of every single one of these responses. What did I do wrong here? I wasn't shifted up all the way. Log of list 2. Okay, so this found all of the logarithms of list 2 for me. Now let's look at a new scatter plot. Okay, so what I'm going to do is instead of doing a scatter plot of the explanatories against the original response, let's do it as the explanatories against the new responses. So we're still going to do a scatter plot of list 1 against list 3. And what do you think of that? Does that still look curved? I think that looks a lot straighter than what we had before. So let's go ahead and draw that picture. So draw the new scatter plot here. So again, we had the normal explanatories, the course, which was list 1. And then what we did is we took the log of list 2, and we put that in list 3. So this is basically the log of the remaining number of M&Ms. Okay? And if you draw the picture, it looks a lot more straight. I mean, it's not perfectly straight, but I would say that's more straight than what is up here. Okay? But can I still say the least squares regression line is this line? I can't, because remember I took the log of these. So here's what we're going to do, is we're going to find the new least squares regression line. So what we're going to do is remember, in my calculator, this is the log of list 2. So we're still going to run the linear regression again. So that's calculate option 8, linear regression. But instead of list 1, list 2, we're going to do list 1, list 3, because list 3 is my new response. Now when it does that, it gives me my new equation of the line. So let's go ahead and write that down, okay? But we have to be careful here. I know that you're probably thinking we should write it as y hat equals 1.76 minus 0.296x, because that's the values in there. But technically it's not equal to y hat. What it's technically equal to is log of y hat, because remember, we took the logarithm of all of the y variables. So I'm still going to write the exact equation down that my calculator says here, but I'm going to write the log in front of the y hat because that's what I did. I took a logarithm of all of the y values in order to calculate this out. Now it says use this least squares regression line to predict how many M&Ms are left after the second course. And actually, real quickly, it doesn't ask you to do this here, but I want to show you the residual plot just to show you that the residual plot is indeed much straighter. Since I ran this, my residuals got restored. So I'm going to put the residuals in my list 4 this time, and you don't have to do this, but here's the residuals for it. So again, to do a residual plot, we're going to do list 1 against the residuals, which now are in list 4. So take a look at that residual plot. You can see that there's nice even scatter now. There's not that curved pattern. Okay, so I'm going to go back real quick just to the least squares regression line. It's a very straight line. And we saw the residual plot had no more curve, which means that now with this logarithm built in here, this is the best fitting line. So let's use this line to predict how many there are left after the second course. Now I know we have that value, but the purpose of a regression line is to make these predictions. So I'm going to take this log of y hat, which equals 1.76 minus 0.296, and since I want to predict it after the second course, well that's what x is, number of courses. So we're going to plug in the second course. And what we're just going to do is type this in. We have log of y hat equals 1.76 minus, we're going to multiply that out, it comes to 0.592. Okay, let's go ahead and do this subtraction here. Log of y hat equals 1.168. But we still got to get y by itself. Y is not quite by itself yet, and I need y by itself to give me the prediction. Well, again, we have to kind of go back to math 3. If you remember how to deal with logarithms, remember a logarithm is a base 10. So what a logarithm is saying is 10 to this power is equal to y hat. I always called it a loop-de-loop in my math 3 class. But in other words, I could say that y hat is equal to 10, because its log is a base 10. 10 to this power is what's equal to the y hat. So you just got to take the 10 and raise it to this as an exponent to figure out what your y hat is. So what I'm going to do is I am going to go to my calculator, and just to remind you, to go 10 to the 1.168, and that's your predicted value, 14.723. Okay, so your y hat, your predicted number of remaining M&Ms, is 14.7. Let's see how close our prediction was. Well, when we actually did it with my son, it was 13. My regression line predicted 14. So that's kind of how we use the least squares regression line when your original scatter plot was not actually a line. What we do is we basically force it into a line using a logarithm, and technically this is a curve. Like if we were to rewrite this and move the logarithm down, or move it around, it would actually create a curve, and I'll show you that another time. But we're basically forcing the scatter plot to be more linear than the curved pattern up here. And as we force it to be linear with this logarithm, we use the equation of the logarithm with a log built in to be our best predictor. Okay, I'm going to stop my video here before showing you the natural logarithm video. So see the next video for the next